Welcome back, let's resume. In the previous video we talked about the setup, the complete setup of hypothesis testing problem. One earlier than that we talked about only the hypothesis. Now we talked about the complete setup and we paid particular attention to something called the level of significance, which is typically denoted in Greek letter alpha. A graphical way to understand it is kind of like this. The area of the red region, as you see in the right hand side picture over here, where my mouse is moving around. This area is the probability of type 1 error, basically. Even though the null is right, as you can see, this normal picture is centered around the null, so we are assuming the null hypothesis. Under that assumption, the probability that we get something like this big, is 0.05. And if my x bar, the sample mean, falls into this red region, then we'll have to reject the null hypothesis and accept the alternative hypothesis, consequently committing the type 1 error. So let's run it again, and let's pause it and run it again. In this case, x bar is too far away compared with the threshold value here, or the critical value. It falls into the red region, and consequently we have to reject the alternative, reject the null hypothesis and consequently accept the alternative hypothesis. But if we do that, even if the null is right, as you can see in this normal picture, you see it is pictured around the null value, then this is going to be the type 1 error. And that's the alpha value. Okay, that was a review, and let's talk about a concrete example problem. Let's go over to example 3.3. And the setup of this problem is something we already dealt with, so we can move in rather quickly, I think. The drying time of a type of paint under specified test conditions is known to be normally distributed with a mean of 75 minutes and a standard deviation of 9 minutes. So this is going to be the mu0 value, and this is sigma. A group of chemists proposed a new additive designed to decrease the drying time. So we are decreasing the drying time. So the new mu will be less than 75, will be the alternative hypothesis. And in the lab test, we got x bar, the sample mean of 72.3, with n equals to 25 observation, the sample size. Now set up the hypotheses and test them with this significance level of 0.02. The area of this red area in the wing part is 0.02. Well, here's the setup. Null and alternative, and then sigma and x bar and alpha. Okay, now that setup is done, let's draw a picture, and picture is always done around the null value. mu0, the null. Alright, we have 0.02 here, the wing part, and we have to find out the threshold, or the critical value. How do we do that? Well, we have to find out the z-score associated to 0.02, and z formula is what? End minus center. Z is end minus center over standard deviation, isn't it? In this case, this is going to be this x, this purple value, this x1 minus center 75 over standard error. But standard error was, as a matter of fact, sigma over square root of n. Let's go over here to get all those Greek letters. Sigma over square root of n. And in this case, sample size is 25, and sigma is 9. And that value has to be approximately the same as the z-score associated to 0.02. So how do you find out the z-score associated to 0.02? Well, here's a normal table, and we want to find out z-score associated to this blue area equals to 0.02 approximately speaking. So let's look for 0.02 around here, and this is what I got. This value is the closest, 0.0202. So approximately speaking, negative 2.05. Negative 2.05 is going to be the equation to solve. And from this equation, flip this denominator to the other side and find out x value. That's going to be the critical value right over here. And compare that with 72.3, the x bar. Yes, 72.3. And then you're going to get the conclusion. Well, here's the computation. X minus 75 over 9 over square root of 25 equals to negative 2.05 approximately speaking. And that's solved for x. It turns out 71.31. And compare that with 72.3 in the picture. This one is 71.31. And where is 72.3? Well, here's a complete picture. 71.30, that's right here. And then 72.3 is over here. It's in the blue region. It's close enough to the null value, so we accept the null hypothesis and consequently reject alternative hypothesis. Let's see. We have sufficient time to do another problem, or as a matter of fact, do the same problem using an alternative method. So let's go ahead and do that. That was the classical approach, which is covered in 8.5. Another way to do it is to do 8.4 method, which we call the probability value approach. The same setup and initial picture, which is a little bit different this time. Centered around 75, well, that's normal. We have to do it around the null value. But instead of looking for the critical value, the threshold, we just consider 72.3 and calculate the area beyond 72.3. And then what do? Compare that with the level of significance, 0.02. The advantage of this method is that you don't have to look up the z-table backward. You can simply calculate the z-score by this 72.3 minus 75 over standard error. Look up the z-table, and then you're going to get this probability p-value, this red area. The confusion comes from the next step. In any case, let's do that. Oh, excuse me, let me keep this picture. And then let's calculate this probability, or the red area. Calculate the z-score, 72.3 minus 75 over standard error. And it turns out about negative 1.5. So look up the z-table for z-value negative 1.5. The probability p is 0.066 something. well, here's the z table. Negative 1.5, where is negative 1.5? Yeah, here we go. 0.0668, approximately speaking. That is the probability. But then again, what does that mean? That means the probability that we end up with some extreme result beyond 72.3, if the null is right, that conditional probability is 0.06 something, which is greater than 0.05. So is it more likely that null is right? Yes, consequently we accept the null hypothesis. The final part is a little bit confusing in this p-value method. Z-score computation is more straightforward and probability computation is straightforward. However, the final step, what does it mean? P is greater than alpha, but then again, what does that mean? Does it mean it is H0 or does it mean it's HA? That part is a bit confusing. At least that was the experience I had when I was grading the students doing this probability method. The students who used the previous method, the threshold method or the critical value method, usually do not get confused because it's pretty much self-explanatory. The X bar is close enough or far away, but in this case it's a little bit confusing. The trade-off is z-score computation, and then p-value computation that follows is straightforward because we're using forward method for the z-table. In any case, here's the complete picture. The probability is 0.0668 something, and that's greater than 0.02. So we reject the alternative and accept the null hypothesis. The final part, you will have to, a lot of students may have to resort to memorizing that, and that can be a bit confusing. Personally, I recommend this method only with a bit of a reserve. Let's go back to the critical value method or solution 1. Same setup, and the initial picture is kind of like this. Around the null value 75 and 72.3 is less than that, so we are looking for left hand side critical value, and that's given by the level of significance 0.02. And then we look up the z-table to find out this critical value, and we end up with this. This value, negative 2.05, is associated to this alpha value of 0.02. Look up the z-table, alpha is 0.02, so we end up with negative 2.05. Solving this equation, we get x value 71.31, which is this value right over here, and that tells you where to put 72.3. Here we go. This value turned out to be 71.3, and 72.3 consequently is to the right, and consequently the sample mean is closer to the null compared with this threshold, the critical value. Consequently, we accept H0, rejecting HA. As far as the understanding is concerned, this method is a little bit more straightforward and a little bit more mistake-free, at least in my experience while grading a lot of papers. The trade-off, by the way, is finding out the z-score backward and solving the equation to get x. So if you are familiar with algebraic manipulation, this is better.